Section: Introduction. In this section, we discuss chain of thought, CoT, a popular technique for prompting language models to reason. CoT helps provide clear explanations for problem solving and is often used to enhance the ability of large language models, LLMs, to tackle complex questions through intermediate steps. Many LLMs, like ChatGPT and Llama 3.1, default to using CoT for reasoning tasks. While CoT is widely applied, it is primarily studied in the context of mathematical reasoning. Most evaluations of reasoning methods for LLMs focus solely on math, with some models claiming to improve reasoning capabilities but only reporting results on math-related tasks. Our findings indicate that CoT significantly aids in problems that require mathematical, logical, or algorithmic reasoning. We observe this trend in both existing literature and our experiments. We note that improvements from CoT are mostly seen in math-related tasks, with a striking 95% of performance gains on certain datasets attributed to questions involving equality. For non-math questions, we find no clear indicators of when CoT is beneficial. To understand why CoT is effective in these scenarios, we break down the reasoning process into two stages: planning, like translating a problem into equations, and execution, performing calculations and deriving solutions. We discover that CoT mainly enhances the execution stage, where computation and symbolic manipulation occur, but it does not match the capabilities of LLMs that use external tools. Our results show that while LLMs using CoT can create and execute formal solution plans better than direct answering, combining LLMs with external solvers yields better results. This leads us to two key implications. First, CoT is often unnecessary for many tasks where it is commonly applied, as more efficient prompting methods can achieve similar results at a lower cost. Second, there is a pressing need to advance beyond prompt-based CoT to more sophisticated methods involving search, interactive agents, or models specifically fine-tuned for CoT. Future research should explore how intermediate computations can be leveraged to address challenging problems outside of math and symbolic reasoning. We also outline the tasks we consider, which involve a question and an answer drawn from a specific label set. One exception we examine is Big and Bench, which uses an LLM to judge and label generated responses. In our approach, we interpret the outputs of LLMs as conditional distributions based on user prompts. We form prompts that guide the model to either provide a direct answer or engage in a chain of thought. While we encourage specific strategies, we find that modern LLMs generally follow these instructions. We ensure that our answer extraction process is effective across different models and tasks, and we have made our prompts and outputs available for further examination. We also explore few-shot CoT prompts, which perform comparably to zero-shot prompts. Section Summary. In this section, we discuss the chain of thought, CoT prompting technique, which enhances language models' reasoning abilities, particularly in mathematical and logical tasks, but shows limited effectiveness in other domains. We find that while CoT improves execution in reasoning problems, it is often outperformed by more advanced tools, suggesting a need for more sophisticated approaches beyond prompt-based CoT. Section: Symbolic Reasoning. In this section, we focus on the significance of symbolic reasoning in our work. We define a problem as symbolic if it can be linked to a recognized formal system, such as mathematics. For instance, the expression 12 times 4 is symbolic because it is grounded in math. Other examples include first-order logic and planning languages. We establish a function that transforms a question into a symbolic expression, which can then be used by a solver to find an answer. In contrast, a question like, "Where on a river can you hold a cup upright to catch water on a sunny day?" is considered non-symbolic because it lacks a clear formal framework for resolution. We see symbolic and non-symbolic reasoning as a spectrum. Our dataset, Musser, is semi-symbolic. It has a formal system for certain parts but also requires common-sense reasoning that doesn't fit neatly into a formal structure. In these cases, we can still create a symbolic expression, but it relies heavily on a language model to generate new information. We also present our central claims, noting that many in the literature believe that performance improvements from chain of thought, CoT, reasoning apply equally to both symbolic and non-symbolic problems. However, our findings indicate that the performance boost is primarily seen in symbolic and semi-symbolic tasks, with little to no improvement, or even a decline, in non-symbolic tasks. To support our analysis, we conducted a meta-analysis of recent papers comparing CoT prompting with direct prompting. We examined all papers from ICLR 2024 and 2 NLP conferences, ECL 2024 and NAACL 2024, filtering down to those that mentioned CoT multiple times, resulting in 516 relevant papers. We further refined this selection to focus on papers that compared CoT and direct prompting, manually extracting key results while excluding certain models and experimental setups. Ultimately, we gathered 1,218 experimental comparisons from 110 papers across 264 datasets, with more details available in our GitHub repository. Section Summary. In this section, we define symbolic reasoning as problems that can be grounded in a well-established formal system, contrasting it with non-symbolic problems that lack such frameworks. We analyze literature on chain of thought, CoT, prompting, revealing that performance improvements are primarily seen in symbolic and semi-symbolic tasks, while non-symbolic tasks show little to no benefit or even decreased performance. Section: Categorization. In this section, we categorize the numerous tasks and datasets we are comparing into 14 distinct categories. We based these categories on the task descriptions and examples, rather than on system performance. Our categorization goes beyond traditional NLP classifications, considering both the format of the tasks and the reasoning involved. We provide definitions for several categories in a table, with full descriptions available in the appendix. Next, we present our results, showing the distribution of CoT deltas, which is the difference in performance between the CoT prompt and the direct answer prompt, across various task types found in the literature. We calculate the average results per paper for each category, represented by blue dots, to illustrate trends across the literature. The categories are ranked by their median CoT delta. We find that the categories that benefited the most from CoT are symbolic reasoning, math, and logical reasoning, with average improvements of 14.2, 12.3, and 6.9, respectively. The average performance for these top three tasks with CoT was 56.9, compared to 45.5 without it. For other categories, the average performance with CoT was 56.8, slightly higher than 56.1 without CoT, but we do not consider this a significant win for CoT. Since CoT requires more computation than direct answering, a fair comparison should account for the computational resources used by both methods. We also investigate whether any non-math datasets benefit from CoT. On the right side of our figure, we highlight the top 10 outliers with high CoT deltas from tasks other than math, symbolic, or logical reasoning. While these tasks are not categorized as math or logic, many are related to logical or mathematical reasoning. The dataset that benefits the most from CoT is Big Bench Hard, which includes problems requiring algorithmic, arithmetic, or logical reasoning. For example, Big Bench Navigate involves spatial reasoning but relies on counting steps, while Big Bench Temporal requires deductive reasoning about event timing. Additionally, legal argument reasoning, categorized as context-aware QA, also demands significant reasoning skills. MMLU Moral Scenarios involves answering two independent questions simultaneously, which combines two simpler questions symbolically. We note a few outliers that do not clearly follow the trend. Science QA includes multiple choice questions across various science disciplines, but it's challenging to interpret performance gains without breaking down results by subject. A dialogue evaluation dataset shows significant improvements with CoT, but since it is proprietary, we cannot generalize. Other datasets like Commitment Bank and tasks involving verbalized confidence also show some benefits from CoT, but these are exceptions. Overall, most reported benefits of CoT in NLP and ML literature come from math or math-related tasks. Our analysis of the literature provides insights into CoT behavior but leaves questions about the latest models and direct comparisons across different model types, datasets, and prompting techniques. To deepen our understanding, we conduct experiments on 20 datasets using 14 models in both zero-shot and few-shot settings to compare performance. In our experiments, we list the models, datasets, and prompting techniques we considered. We focused on English models that are commonly used and benchmarked on general reasoning datasets, excluding math-specific and non-English models. We also concentrated on instruction-tuned language models. Our datasets include those frequently used in CoT and reasoning literature, covering a mix of non-symbolic, semi-symbolic, and symbolic reasoning. They come in various formats, primarily multiple choice and short answer, as CoT is not typically applied in long-form responses. We categorize each dataset based on the reasoning required to solve it: common sense, knowledge, symbolic, mathematical, and soft reasoning, with soft reasoning involving common sense and natural language beyond simple inferences. Finally, we explore several prompting strategies to elicit reasoning from language models, noting that past research highlights the importance of prompts. However, we generally observe only slight performance differences, so we focus on prompts suitable for zero-shot and few-shot settings, making adjustments to enhance the model's ability to produce clear answers. Section Summary. In this section, we categorize various NLP tasks into 14 groups based on their descriptions and reasoning types, revealing that tasks related to symbolic, mathematical, and logical reasoning benefit the most from chain of thought, CoT, prompting. Our experiments across 20 datasets and 14 models indicate that while CoT shows significant improvements in these areas, the overall benefits for non-math tasks are limited, with most gains observed in math-related contexts. Section: Implementation Details. In this section, we describe our implementation details. We utilize a high-throughput inference package called VLLM for the model inference process and apply greedy decoding across all models. Our prompts are primarily sourced from the Llama 3.1 evaluations, with minor adjustments made for consistency. For other datasets, we either adopt the standard prompts from the original papers or create our own. Each dataset and model has a customized answer parser. More specific information about the datasets, prompts, and answer extractors can be found in the appendix. We investigate where zero-shot chain of thought, CoT, improves upon direct prompts. We find that CoT enhances performance on datasets requiring math or formal logic, such as Math and Context Hub. The left figure illustrates the average performance improvement across reasoning categories, while the right figure shows the performance gains from using CoT for each dataset, averaged across all models. In contrast, for datasets focused on common sense reasoning, language understanding, and reading comprehension, we observe little to no difference between zero-shot CoT and direct answers. However, mathematical and symbolic categories see significant improvements, with Math and GSM-8K showing gains of up to 41.6% and 66.9%, respectively. Semi-symbolic datasets like Context Hub and Musser also show moderate improvements. All results, including numeric data for both CoT and direct answers, are detailed in the appendix. We also explored the few-shot setting, which had minimal impact on the effectiveness of CoT. Next, we examine whether the answer format affects the benefits of CoT. We find that it does not significantly impact performance. Free response capabilities may be limited by the need for pre-planning or reasoning. Many datasets, especially those not focused on math, are multiple choice. We note that CoT performs similarly to direct answers in two non-multiple choice datasets requiring varying levels of non-symbolic reasoning. In Musique, a semi-symbolic dataset with multi-hop reasoning, we see no overall improvement from CoT. For BigNBench, which uses free-form responses, we created a CoT prompt that asks the model to generate a plan and then the full response in one go. We evaluate these responses using GPT-4o Mini as a judge. We exclude certain prompts that ask the model to think step by step to maintain comparability with direct answers. The performance of BigNBench is plotted based on the number of responses scoring 4 or better, showing mild overall improvement from CoT. Finally, we assess whether the gains in knowledge, soft reasoning, and common sense are significant. Generally, they are not, except for MMLU, Strategy QA, and Musser. We tested the significance of CoT improvements across 13 datasets in these categories using paired bootstrapping and applied a Bonferroni correction for multiple comparisons. About 38% of the datasets showed significant benefits, with nearly half of these comparisons coming from MMLU and MMLU Pro. Strategy QA and Musser also demonstrated consistent performance boosts across multiple models. The remaining datasets with significant benefits are varied across the models. Section Summary. In this section, we describe our implementation details, utilizing the VLLM inference package with greedy decoding and tailored prompts for various datasets. We find that while zero-shot chain of thought, CoT, prompting significantly improves performance on mathematical and symbolic reasoning tasks, it shows little to no advantage on common sense and language understanding datasets, with only a few exceptions like MMLU and Strategy QA. Section. Zoom in, MMLU and MMLU Pro. In this section, we examine the performance of chain of thought, CoT, reasoning on the MMLU and MMLU Pro datasets. We notice that while CoT improves results, the datasets are too diverse for straightforward analysis. To better understand how CoT performs across different categories, we analyze its effectiveness in reducing errors for Llama 3.1 models, both 8B and 70B, and identify the top 3 categories where CoT is most beneficial. Some of these categories are inherently mathematical, which aligns with our expectations. Interestingly, we also find that CoT aids in categories like business, where math is often involved, such as calculations related to wealth. We recognize the need to analyze MMLU at a more granular level, allowing us to test our hypotheses with greater precision than broad task groupings permit. Our goal is to create a classifier that predicts whether CoT will be helpful for a given question. Specifically, we want a function that returns 1 if the extracted answer matches the correct answer and differs from another generated answer. We explored various forms of this function but found that the most effective approach involves considering both the question and the generated answer, particularly focusing on whether they contain an equals sign. The presence of an equals sign strongly indicates the involvement of equations, which is a key feature of symbolic reasoning. We plot the performance differences of CoT against direct answers for both MMLU and MMLU Pro, categorizing them based on the presence of an equals sign. Our findings reveal that most performance improvements from CoT arise from questions that include an equals sign, suggesting that CoT primarily benefits math-related questions, with minimal gains for non-math questions. We also discuss the strengths and weaknesses of CoT in formal reasoning. We establish that CoT is particularly effective for symbolic reasoning tasks, and we break down these tasks into 2 stages, planning and execution. In the planning stage, we extract variables and define their relationships, while the execution stage involves using a solver to derive the final answer based on the plan. By separating these stages, we can assess how much a language model benefits from merely having a plan versus being able to reason through it with CoT or using an external solver. To evaluate the effectiveness of the language model, we compare different settings, including few-shot direct answers and CoT prompts, as baselines. We include examples of each setting to illustrate our findings. Section Summary. In this section, we analyze the performance of chain of thought, CoT, reasoning on the MMLU and MMLU Pro datasets, finding that CoT significantly improves results primarily on math-related questions, as indicated by the presence of equations. We propose an instance-level classifier to better understand when CoT is beneficial, revealing that its effectiveness is largely tied to tasks involving symbolic reasoning, which we break down into planning and execution stages. Section. Settings 3 and 4. Plan plus direct solver and plan plus CoT solver. In this section, we explore two settings: Plan plus Direct Solver and Plan plus CoT Solver. We draw inspiration from previous strategies to create a symbolic plan. Specifically, we use a few-shot prompt designed to generate a formal specification that can be executed by a symbolic solver. In this prompt, language models are tasked with solving the generated specification and deriving the final answer, either by directly providing the answer after generating the specification, Plan plus Direct Solver, or by offering a step-by-step explanation of the plan, Plan plus CoT Solver. Here, the specification for math datasets is a Python program, while for logical reasoning datasets, it consists of formal specifications in first-order logic. Next, we introduce setting 5, Plan plus Tool Solver. We assess how well the CoT method performs symbolic computations compared to external symbolic solvers. Following previous research, we generate the plan in the same way as in the CoT solver, but we now input the plan into a symbolic solver, such as a Python interpreter or an SMT solver, to find the solution. For our evaluation setup, we compare the performance of each setting on math and formal logical reasoning datasets. We acknowledge that recent large language models may overfit due to data contamination, so we include a harder version of the dataset to mitigate this issue. For the Plan plus Direct Solver and Plan plus CoT Solver, we utilize few-shot prompts, while for the Plan plus Tool Solver, we apply advanced prompting methods with symbolic solvers. Specifically, we use a program-aided language model that executes the generated plan with a Python interpreter and a satisfiability-aided language model that employs an automated theorem prover to solve the specifications. If the generated plan cannot be processed by the tool, we resort to random guessing for multiple-choice questions and mark them incorrect otherwise. In our evaluation results, we present findings across various models. We observe that simply having a plan does not significantly enhance performance compared to direct answers. Strong performance often requires the CoT or Plan plus CoT Solver methods, especially for math-heavy datasets. Although CoT and Plan plus CoT Solver show improvements over direct answers, they are generally outperformed by the Plan plus Tool Solver. This suggests that language models struggle with executing and tracking steps compared to symbolic solvers, highlighting why CoT is beneficial for symbolic tasks. While all tasks could potentially benefit from detailed problem-solving descriptions, CoT only excels when substantial tracing and computation are involved. Thus, we recommend pairing language models with symbolic solvers for better performance on symbolic tasks. We also investigate where CoT is effective and why. Our findings indicate that CoT improves performance in math and logic, aligning with earlier work on CoT for language models. As CoT gained traction, its use expanded to tasks that typically do not require multiple steps, often yielding slight improvements over direct answers. However, our results reveal a distinct difference in performance between non-symbolic and symbolic tasks. While any question could theoretically benefit from deliberation, CoT seems to primarily aid questions solvable through symbolic manipulation. We note that not all tasks can be translated into executable plans, and for some datasets, the benefits of CoT are minimal. We leave the exploration of whether specific deliberation methods could enhance performance on non-symbolic tasks for future research. Section Summary. In this section, we explore various settings for generating symbolic plans and solving them using different methods, including direct solving, chain of thought, CoT, reasoning, and tool-augmented approaches. Our findings indicate that while CoT improves performance on symbolic tasks, it is generally outperformed by tool-based solvers, highlighting the importance of combining language models with symbolic solvers for optimal results in mathematical and logical reasoning. Section: Long Horizon Planning. In this section, we discuss long horizon planning, a task where symbolic reasoning is particularly beneficial, although we haven't explored it extensively in our experiments, except for Big and Bench. We have two main reasons for this. First, our focus is on language-based tasks, which tend to involve simpler planning. Second, there has been considerable debate about the effectiveness of chain of thought, CoT, methods, both in support and against them, leading to the development of complex systems aimed at improving planning solutions. While generating and interpreting stories involves some planning with natural language, these tasks are not typically formalized or benchmarked as planning and reasoning. We also consider whether we can enhance CoT further. Our work examines CoT variants that do not rely on multiple inferences. However, there is some evidence suggesting that making additional calls to large language models, LLMs, can be beneficial. A challenge we face is that these methods require significantly more computation, and careful benchmarking sometimes shows that simpler techniques perform just as well as more complex ones. Nonetheless, previous theoretical findings indicate that CoT fundamentally enhances transformers, suggesting potential for improved CoT variants beyond just prompt-based approaches. Additionally, recent methods that benefit from internalizing CoT imply that the explicit generation of intermediate tokens may not be fully utilized yet. We also acknowledge a limitation in our study regarding potential data contamination. It is unclear which benchmarks may have been specifically pre-trained on by language models. If a model has memorized answers to benchmark questions, we would expect it to perform better in direct answering, thus narrowing the gap with CoT, as it could simply reproduce known answers instead of deriving them. However, we believe our overall conclusions remain reliable for 4 reasons. First, we utilize a variety of language model sizes, including smaller models that are less likely to memorize. Second, datasets that perform poorly in direct answering, like GSM-8K hard, are unlikely to have been significantly memorized. Third, the inclusion of recent datasets such as Musser and BigNBench helps mitigate this risk. Finally, our literature review includes papers presented at conferences in 2023, showcasing a range of older LLMs trained at different times.